Seminar of Nexus Summer 2024. Today we are having Krishnakant with us. Welcome to another seminar of Nexus Summer 2024. Today we are having Krishnakant with us, and he will be giving his talk on linear algebra and its application to quantum mechanics. Now, Krishnakant, over to you.
Okay, thank you, Devang. So, first of all, thanks to the organizers for giving me the chance to speak on the topics. So, let's begin the wasting time. So, we will. Okay. So, the motive of the talk is we will. We will deal with the basics of the linear algebra and the applications of linear algebra in quantum mechanics. So, before starting, the topics that will be covered in this talk will be some. I will introduce you with the field and vector spaces and its properties of vector spaces. Then we will go further on inner product spaces, then its properties, and we will go on eigenvalues, eigenvectors, diagonalization, hermiticity, and its application in quantum mechanics. So, before introducing you with the vector spaces, I will introduce you uh, uh, with a brief introduction of linear algebra. So, what's linear algebra is? Linear algebra is a branch of mathematics that deals with the vectors and vector spaces, also called the linear spaces. So, we will deal with the linear transformation system of linear equations, and it is the fundamental for many areas of mathematics and applied sciences. So, some key concepts that we will discuss in this talk within linear algebra will be written as. So, vectors we know this, and we have learned about this in our intermediate. So, we will deal with vector spaces and matrices, system of linear equation and determinants, all already done in the intermediate. So, these are the basics. So, I will not go on these topics. We will discuss eigenvalues, eigenvectors, inner product spaces, and orthogonality and orthogonalization. Then, what are the basics? What are the application of linear algebra in general sciences and in our day-to-day life? Linear algebra is widely used in the various fields such as physics, computer science, engineering, economics, statistics, and more. So, essential for the machine learning, computer graphics, and optimization, and further on many studies and quantum mechanics, and further on there are many applications of linear algebra in our. So, let's introduce you to the field. So, what is the field is? A set F is called a field if A and B belongs to F. If we assume F contains an elements of set this type A, B, C, and C, D, A, B, C, D, and other elements. So, if set of elements alone endowed within boundary of law of composition of its elements. So, what the two laws are? First, we will do the one denoted by the addition, and the second denoted by dot that is called the scalar multiplication. So, what are the properties of field will be? So, if we consider A and B be the elements of vector space, elements of field. So, A plus B should belongs to the field. So, A plus B should belongs to the field, and then next one A minus B should belongs to the field, and A dot scalar multiplication of the both the vectors should belongs to the field, and at last division of the of these numbers, just if we assume A by B. So, if we do the division, then it should belongs to the field F. So, mention that B should not be equals to 0. So, let introduce you to the vector space, and so the set any set, if we consider any set consisting of elements u, v, and w, so let v be an empty set and f be a field. So f be a field. Then we together with two operations, we will go with the two operations that the if we consider v1 and v2 are the elements of vector space, and we should read any vector we will read as vector space over a field f over field over a field. So these conditions should be satisfied if these conditions should be satisfied if we these conditions should be satisfied. So suppose v1 and v2 belongs to the v over v vector space over field f, and there should be a law of vector addition. V1 plus v2 should also belongs to the vector space over a field. So suppose then the next one should be v is a vector v is a vector that belongs to the vector space v, and alpha is the scalar which belongs to the field f. Then sorry, there is a mistake. So alpha dot v, yani that's mean a scalar product of alpha and v, means the scalar multiplication of alpha and the vectors and the vector v should belongs to the vector space over a field f. So this is called the law of vector addition. Mention that elements of f is called the scalars and the elements of v are called the vectors. So note that. And now next we will discuss about the properties of vector spaces. So you all know commutative, what commutative is. If we change the order, if we change the place of the, just like u and v should belongs to the vector space v, and u plus v should equals to v plus u. Then associativity, you all know. Mention that a and b. Here you can see that these a and v are the scalar. These belongs to the field f, and you can see u, v, and w are the vectors which belongs to the vector space v. So then next is the additive identity. There exists an element 0. If we consider an 0 will belongs to the vector space v, then additive identity of v plus 0 should be equals to 1 second. So v plus 0 should v plus 0, if we add any 0 to a vector space, it should be the same. So the next one is additive inverse. So if there exists if there is an element v belongs to the vector space v, and there should be there exist an other element, that is I'm considering it w, that should belongs to v, such that both the addition of these vectors should be equals to 0. So the next one is multiplicative identity. If we multiply any vector with 1, then the same vector will be returned. So mention that v should belongs to the vector space v. Now let's move on to the inner product spaces. So vector space v over a field f, where f is the field of real or complex numbers. F can be the field of real. Here the f can be the field of real or complex number. And they becomes an inner product if every pair of the elements u and v, there is associated a unique scalar belonging to the field f denoted by u and v. Then these are called the inner product or the scalar product is also known as the scalar. Inner product is also known as the scalar product of u and v. So there are three conditions on which the inner product is considered. So these are the properties. Here you can see that u and v, if we do an operation between u and v, and such that u and v should belongs to the vector space v, and there exists a complex conjugate, which is denoted here. You can see the asterisk sign is denoted as the complex conjugate. Now here are some properties. So here are the properties, and so Now, properties of inner product spaces. So if we take the scalar product of a vector with itself, we will find that you should notice this. This is called the norm on the vector V. The inner product induces a norm on the vector spaces defined by this. So if you can see here, the square root of this quantity is defined as the norm of the vector space V, denoted by this sign. So we can see here that um, this is the length. You can see this. This denotes the length, or we can say the magnitude of a vector, and mention that if the norm of a vector is unity, if we solve this and we got a unity, it is called the normalized vector or a unit vector itself. So and now we will move on the orthogonality. So two vectors u and v are orthogonal if we perform any operation between them should be equals to 0. Sorry, not any operation, only the scalar product. If the scalar product of the two vectors is 0, then the vector is said to be the orthogonal to each other. Thus, two vectors u and v, if we assume that u and v, and these conditions get satisfied, shit, yeah. This is called the if the operation between u and v is 0, then only if and only if the condition get if and only if this condition gets satisfied, the function is called the orthogonal function. So if we so if we make a set of these orthogonal vectors, and uh, if we make the set of all the orthogonal vector, then it is called the orthogonal set, and each vector is normalized to unity. If we perform this action and normalize it to the unity, so it is called the orthonormal vector. So next is the Pythagorean. So you can see here is the norm of the two vectors, the norm of the addition of two vectors is equal to the norm of uh, uh, norm of the square of the both vectors separately. So according to the if we open this bracket, so if we solve this equation, so you will get u square plus v square plus 2uv, and you will see that here is the scalar multiplication of 2u and v. U and v is the scalar multiplication. We will get it 0, as we have assumed that orthogonal vectors, as u and v are orthogonal vectors. Now, hello, can we continue it 10 minutes? Hello,
Yes, sir.
hello.
Yes, yes, we can hear you.
Can we continue it in 10 minutes? बारिश होने लगी है.
Okay.
So, what's the Pythagorean theorem is if we solve u square plus v square on the bracket. So, on solving this context, so we will get u square plus v square plus 2u and v. And here we can see that u and v are in the scalar multiplication. So we have considered u and v as an orthogonal vector, and the scalar product will get 0. So we will get this result. So we will get this result. Now moving on to the next property of inner product space. Let assume u and v with an arbitrary vector in a vector space. So we what the Cauchy-Schwarz inequality says that if you perform any action, this action between two vectors, arbitrary vectors u and v, which inverts this equation forms the norm on the v norm on the this inequality says the norm on the u and the norm on the v, if we put them on scalar multiplication, and then mm, we can say in words, we can say the absolute square of the inner product of two vector is less than or equals to the product of the squares of the is equal to the product of the squares of their norms. So the what the norm is, the square root square root. So what the next one is the triangle inequality. If we assume u and v with the vectors inside a arbitrary vectors in a vector space. So if we perform, we can if the norm on the vector u, if the norm on the addition of the vectors u and v should it will get equals to or less than with the norm on the u and v separately. So we are just doing the overview of these properties, but have more significance and are more deep and further. So next, moving on to the eigenvalue and eigenvectors. So we all have the prior knowledge of matrices, determinant, and system of linear equations. So further on, we will go on eigenvectors and eigenvalues. So if we consider a square matrix A and a non-zero vector of V, and see that V is an eigenvector of A if this equation gets satisfied, a scalar product of A and B should equals to the lambda. Lambda is a scalar, and the lambda is the eigenvalue corresponding to the eigenvector V. So here is the V is the eigenvector, and the lambda is the eigenvalue for the corresponding. So next, what's the eigenvalue equation? The equation written on above is the eigenvalue equation, and we will if now the next one is the characteristic polynomial, and the eigenvalue of A are found by solving the characteristic equation, and the lambda be the scalar, and the here if we solve the characteristic equation A, B, and matrix, and if we multiply lambda in an identity matrix and subtract them from the original matrix, and the determinant of this matrix should be put equals to 0, we can get the values of we can get the eigenvalues that is lambda maybe 1, 2, or 3. So what are the properties? One is the most important. So and if we consider the matrix is of n into n order, so the at most eigenvalues can be n, meaning that it will not exceed the order of the matrix. So the next one is eigenvectors corresponding distinct eigenvalues are linearly independent. So linear independent describes is linear independent can be described as the relationship between the vector space and relationship between the vector in a vector space. So next one is the eigenvalue can be real or complex. If we even if we had a matrix of the real entries, so consider here matrix A consisting of 2, 1, and 1, 2. So if we wants to find the eigenvalues, so we should subtract the lambda I from this equation and finding the determinant, and further on we can get the eigenvalues. So next one is diagonalization. So diagonalization is the process in linear algebra where a square matrix A is expressed in the terms of its eigenvalues or eigenvectors. Here we can see that A is the original matrix and P is the what? P is the eigenvector equation, matrix of eigenvector, and D is the matrix of diagonalization. And here is the P of inverse. So if we are able to define this equation, if we are able to prove this, then we can say that the matrix is diagonalized. So let's have a look on this. That how can we prove a matrix to be diagonalized? So first step is finding the eigenvalues. So we have done that, putting that matrix into putting that matrix and finding the eigenvalue of A, then finding the eigenvector. So for each eigenvalue lambda I, lambda can be lambda 1, lambda 2, lambda 3, and further on. So solve the equation, this equation. If we subtract lambda, that's the equation that the equation here we can see going further on and putting that equals to 0. So we can get the corresponding value of V, corresponding value of eigenvectors, that is V, with respect to the lambda. That's if we get a lambda 1 and putting that into this, and we will get an V1 and further on. So what we will form the next step is we will form the matrix of eigenvectors V1 and V2 as columns. Mention that as columns we will form the uh, matrix of eigenvectors. Then form the matrix of diagonalization, which where we will put the eigen where we where we will put the eigenvalues lambda 1, lambda 2, and up to lambda 3 and as a diagonal. So on the diagonal. So then we will verify that, ensure that P is invertible. Mention that. So we have to find here the inverse of the P, and that mention that P is invertible, and that P, that means that P should not be determinant of P matrix, that is the eigenvalue matrix, should not be equals to 0. And then the relationship, then prove this relationship, we will verify or prove that the matrix is diagonalized. So next, move on the property of hermiticity. So a matrix A is said to be a Hermitian matrix if it is equals to its own conjugate transpose. If we here you can see, if here is the done A is a matrix, and A is mentioned that A is the Hermitian matrix and it satisfies the given conditions. So here we can see that this A and A to the power dagger, so denotes that conjugate transpose. This is the conjugate transpose of the original matrix A, and also called this is also called the Hermitian transpose of A. And this means for any Hermitian matrix A of the elements of ith row and jth column is the complex conjugate of elements in the jth row and ith column. So we will get directly can get this equation. So sorry, there is a mistake. So here will be Aij should equals to the conjugate complex of Aj. No, sorry, that's correct. Here is the mistake at the down. So where Aji is the conjugate complex of Aji. So next, move on to the a real symmetric matrix is a special case of Hermitian matrix where all elements are real. So if we do the transpose of this matrix, consider, so we will get the same as the original matrix. So we can say that A should equals to the transpose of A. And if we consider a complex matrix, that is that's having iota and negative iota. So if we perform, then B then B should be equals to the conjugate complex conjugate of the B, and we can prove that B is an Hermitian matrix. So now moving on to the application of quantum mechanics. So quantum mechanics heavily relies on the linear algebra concepts, and including vector spaces, eigenvectors, eigenvalues, and diagonalization and hermiticity. So these are the mathematical tools that are essential for understanding and describing the quantum system. So moving on these applications, we have quantum states. So what's the quantum states are? Quantum states are the fundamental description of physical system of quantum mechanics in quantum mechanics. These are the fundamental systems. So these are the you see that here is the symbol that is pronounced as cat psi. So and if we remove that this arrow and this r angle from this, the remaining psi is called the we can say that it is the superposition. So uh, let's move on to the superposition principle of quantum mechanics. So quantum states can be superimposed if we can see here, and that cat psi 1 and cat psi 2 are the states, and then here we can see that cat psi, this cat psi is a combination of the states of psi 1 and psi 2, this cat psi 1 and this cat psi 2. The coefficient C1 and C2 that we are seeing here, these coefficient of coefficients, both the cat psi 1 and C1 and C2 and psi 2, cat psi 2, uh, determines the contribution of each state and overall state. So if you if let's go with an example. If you consider an example of qubits 0 and 1, so you can put psi 1 as the 0 and psi 2 as a 1. So the equation will be cat psi equals to c1 psi 1 c1 cat of 0 and c2 cat of 1. So on further on solving this, we will easily get that cat of alpha square and cat of beta square equals to 1. So what are the let's move on to the application of quantum mechanics and application of inner product in quantum mechanics. The inner product that we can see the equation here, and defines the probability amplitude between the state with more important implications for the measurement and probability. Let's move on further on the eigenvalues and eigenvectors. What are their uses in quantum mechanics? So operators in quantum mechanics correspond to the physical and observable, like position, momentum, and energy. The eigenvalues and eigenvectors of these operations are crucial for several reasons. So if we see an part of this, so we will see that an observable associated with an operator A hat. This is pronounced as, I think, A hat. So the eigenvalues of A hat represent the possible measurement outcomes. So maybe A hat's pi cat pi and should equals to this, and then lambda is a possible measurement outcome. Lambda is a possible measurement outcome when the system is in the state of cat pi. So let's move on to the application of diagonalization in quantum mechanics. So we can see the Schrodinger's equation has h hat in it. So this is the Hamiltonian governed by the Hamiltonian h bar h hat. So diagonalization can help us can help us to understand the time evolution in a simplified way. Mm, and so hermeticity. So what's the, we have discussed in this in the previous, and if we see the evolution of quantum states we can say that evolution of quantum states get more simplified using quantum uh, get diagonalization using diagonalization. So let's move on to the hermeticity. Observables and quantities we have discussed above, that operators representing physical observables, position, momentum, and energy must be Hermitian to ensure the real measurement. And further on this, the hermeticity ensures the eigenvalues. Hermeticity.
Yes, go on.
So the last one is orthogonality. So the orthogonality has many applications in quantum mechanics, uh, as the eigenvectors of Hermitian operators correspond to the different eigenvalues are orthogonal, which is an important or for which is important for the probabilistic interpretation of quantum states, and uh, it has many applications in quantum mechanics, just like eigenstates and eigen we have discussed, and ensuring the completeness of the eigenstates. The orthogonality also help us to ensure the completeness of the eigenstates. So and also in projection operators and quantum interference and time evolution in orthogonality. And further on, there are many uses of uh, and there are many applications of linear algebra in quantum mechanics. Uh, a simple, mm, I have covered very a small amount of applications. So thanks for paying attention, and thanks for your coordination for this stuff.
Yeah, thank you. Anybody has any questions for Krishnakant?
Hmm?
No, I'm asking if anybody has any questions for Krishnakant. Okay, then let me ask some. Go to the sorry, please go F5, Krishnakant.
Hmm?
Please have it on slideshow F5.
I'm not able to hear you, so repeat again.
So go to the previous pages. There was a page where you have shown there's a complex matrix
Okay.
pages. Yeah, yeah, yeah. No. You actually it was somewhere. Go forward maybe or backwards. I don't know. There was a complex matrix, and you have shown the complex conjugate of that matrix. And I don't think so. It was right. Can you go to that page? Maybe do the F5 palette. Have it on slideshow. It will be easier to move. Anyway, I was just wanting to point that was wrong with, because that was not completely equal. You did not conjugate it. It was just transposed. You had to conjugate it. And actually, this is right.
Okay.
This implies, yeah. And on the slide you have said the GI is wrong. No, this is right. This is how you define hermeticity. And those operators which satisfy these conditions are called Hermitian. And a Hermitian operators, when they act on some certain eigenvectors, they always have real eigenvalues. So in one of the slides, we have said that these are important in quantum mechanics. So speaking from physics side, yes, it's very important to have real measurements. Yes, that's why you only use Hermitian operators, because that will give you the real measurements. For example, Hamiltonian gives energy. Hamiltonian is an operator which gives energy of a system. That system is described by psi. As you have said, psi is a function. Wave function, it is describing some system. So any operator, when you act on this psi, will give out some eigenvalue. That is your measurement. So there's something called position operator. Position operator acting on some state psi will give you position. Momentum operator acting on the state psi will give you the momentum. Hamiltonian operator acting on the state psi will give you energy. Similarly, there are many operators. And yes, of course, linear algebra helps you to understand all of these. So if an operator is not Hermitian in quantum mechanics, it's not useful. Okay.
Okay.
Yeah, and for Hilbert space is just some vector space with some inner product. Inner product defines a metric in mathematical terms. Yeah. Anyways, yes. Yeah. Good talk.
Thanks.
Yeah. If anybody else has questions, okay, then hello. Thank you. I will end this meeting now. Thank you for the talk. Okay. Bye. See you.